So to get started, I just want to give a big thank you to all of our sponsors. So first, a big thank you to Netflix, who is a premier sponsor of Code this year. A big thank you to our event sponsors, so Amazon, Booking.com, and StatSig. And also a big thank you to EPO, who is our reception sponsor. I encourage you to visit the sponsor room if you're on the hunt for job opportunities or maybe some swag. I feel like there's usually some swag floating around in the sponsor room. That's located just next door in the room to my right. Would also like to give a quick thank you to the technical program committee. So these are the folks that read all of the abstracts that people submitted, sifted through them, and put together the really fantastic program that we have over the next couple of days. So that's Jennifer Allen, Madhav Kumar, House Lin, Sahil Lumba, Alex Mooring, Peyman Shahidi, Hongyi Tuye, Emma Wiles, and Yuan Yuan. Finally, I'd like to thank the other organizers of the conference who are not up here at the podium right now, many of whom you will see over the next couple of days, moderating panels, introducing plenary sessions, things like that. So that is Sinan Aral, Dean Eccles, John Horton, and Sandy Penland. All right, so a couple of general announcements. Sorry, this is a lot of front-loaded logistical stuff before we actually get into the interesting experimentation talks. So we are recording all of the sessions that happen in the plenary sessions. That's talks like the ones that Johan and Sida are about to give, and also the panel discussions that myself and Dean will be moderating. Those are all going to be posted to the MIT IDE YouTube at a later date, but we're not recording any of the poster slam presentations or the parallel talks. So if you are giving one of those talks and are worried about your talk being posted online, don't worry, it's not happening. You can also find a QR code on the back of your event badges that allows you to view select abstracts for the talks that are being given at the conference. That QR code is also visible on the screen up here. So if you see a talk that really scintillates your mind, I encourage you to go check out the abstract for that talk by visiting that QR code. And finally, if you are posting on social media about the conference on X, FKA Twitter, or on Threads, or on TikTok, or whatever the case may be, I encourage you to use our designated event hashtag, which is hashtag CodeCon24. All right, in terms of the plenary sessions, such as the one that I'll be moderating in a second, all of them are going to happen in this room, which is labeled on your programs as the salon. Each plenary session is going to talk for 25 minutes, and then we'll take one or two clarifying questions while we transition. After both people have presented, we're going to have sort of like a Q&A panel type thing up here. I'll ask a couple of questions, and then we'll open it up for the entire room. So if you don't get to ask your question in that transition moment, don't despair. We will have people out in the room running around with mics, allowing you to ask your questions later on. For the plenary sessions and the panels, please ask your questions via microphone. As I mentioned earlier, we are going to be posting these online, and so having your voice amplified is helpful so that the video that appears later on isn't weird. All right, in terms of the parallel session flow, all of those sessions are going to happen downstairs in one of 3 breakout spaces. They're all located on that floor below us. And then some parallel sessions will also happen up here. So they're either going to be downstairs or up here. Staff in the foyer will help you find the room. One thing to note is that for today, we do not have all of the rooms downstairs. We only have the rooms that are to my left, to your rights. If you're more of a geographically minded person, we have the rooms to the west side, but not to the east side. So keep that in mind. There's another event that's happening downstairs in those other rooms today. One thing to note is that the other event downstairs has food, and we really don't want code attendees pillaging the food coffers of the other event. We have a lot of food up here for you to eat, and so at least for today, if you're looking for food, drinks, refreshments, things of that sort, they are all located up here on the 7th floor, not on the 6th floor. So just please keep that in mind. During the parallel sessions, each speaker has 12 minutes to present your work. Similar to up here, in between, we'll take a question or two. After everyone in the session has presented, whoever is chairing the session, that person will probably introduce themselves to you before the session starts. We'll open the floor to questions, and there'll be sort of a panel type thing. If you're in the audience during those parallel sessions, I really encourage you to try to find questions to ask that kind of span different papers in the sessions. I think that's generally pretty fun. One last note is that to everyone who is a plenary or parallel speaker, report to that room at the very start of the break before the session to just check in with AV and that session chair. And AV has all the slides that have been submitted. If you are presenting over the next couple of days and you didn't submit your slides, please head to registration now so that we can make sure that we have the slides for your session. All right, I think I have one more thing. Yeah, all right, one more. Sorry, bear with me, please. So the poster presentations that are going to be happening during lunch today and tomorrow. So we had so many amazing submissions to code this year. We even had to decline a lot of really fantastic talks that we otherwise would have wanted to accept. And so in addition to the parallel presentations, we have a lot of really fantastic posters, and those are going to be presented during lunch today and tomorrow. So we're going to have those during lunch. Today we'll see posters 1 through 18. Tomorrow we'll hear from posters 19 to 34. During these poster slams that occur during lunch in this room, each presenter is going to be given 2 minutes each. They're going to pitch their work. There'll be a line up here at the front of the room in the order that the papers appear in the printed programs. People will speak from the podium up here, and after they speak, they'll kind of, exit the stage and make their way back to their seat. We're going to start that 15 to 20 minutes after lunch. So hopefully that'll give everybody time to get food, bring it back to your seat, chat a little bit with your friends that are seated nearby before we actually start the presentations. At the end of the day, both today and tomorrow, during the receptions, there's going to be essentially time to go look at the posters, speak to the poster presenters. So think of the slams during lunch as essentially the trailer for the feature film that is the poster presentations during the reception. So all poster presenters should report to this room during the afternoon coffee breaks. So today those are at 2:20 p.m. and 3:35 to pin your posters to foam poster boards and get set up on an easel. We're providing the easels, the foam boards, the thumbtacks, and then you'll be all set for the presentations later on today. So just to clarify, all poster boards will be displayed today and tomorrow, regardless of which day you're kind of giving that short poster slam presentation for the poster. So be prepared to stand by that poster during both sessions today and tomorrow in case people are interested in your work. Okay. That is the end of the laundry list of logistics. Hopefully you're all awake and not asleep. If you did fall asleep, there's coffee in the room outside. But now I'm really excited to introduce to you our first set of plenary speakers. I personally am very excited for both of these talks. I hope that all of you are as well. Our first speaker is going to be someone that I've known for a long time. I'm a big fan of his work. Johan Ugander, who's an associate professor at the Stanford School of Engineering. He's going to be presenting on counterfactual evaluation of peer review assignment policies. And so without further ado, I am happy to introduce you to Johan.
Thank you, David. Thank you to the organizers. It's always a delight to be here. The weather's cooperating, et cetera. I also get to be the guinea pig for the tech, so let's just see forward, backwards. Backwards. Great, okay. Hey, everyone. I've been working on causal inference and sort of systems involving complex human behavior and algorithms for a while. And today I'm going to be talking about a project that's actually had, over the last 2 years, two preliminary talks at Code. One about sort of like this peer review context, and then one about the methodological challenges that we ran into. Both of those are now papers that have appeared at NeurIPS and ICML respectively. They were led by Martin Savesky, who actually met at Code many years ago. He came up to me and asked some very technical questions about a paper, and then a few years later I hired him as a postdoc. And then he led this work, and he's now on the faculty at the University of Washington. So it's sort of a story made at Code. And then Stephen Jackman, who's recently defended his PhD at CMU, Nihar Shah, who's faculty at CMU, who studies peer review systems very extensively, and then Samir Khan, who's a Stanford PhD student who recently defended and joined Meta. So the problem for those of you who are not active in the computer science literature is that computer science runs these enormous conferences. So you have these situations where you have more than 8,000 submissions is sort of common. There's many conferences across machine learning systems, et cetera, that operate at this scale of sort of like thousands and thousands of submissions. And then also they have thousands and thousands of reviewers. So you have something like 8,000 submissions, 3,000 reviewers, and you're trying to match papers to reviewers. So the advanced versions of these systems that we'll be talking about today, they do text analysis of the submissions that have been sent in. They do text analysis of the publication history of the people who are impaneled to be reviewers. They also consider the bids of the reviewers, and they mash this all together to some sort of score that they're trying to find an optimized match. They're trying to figure out, like, what is a match that will give people papers that they know the vocabulary of or that they want to review in various combinations. And so, in a simple example here, we're going to set this up and we're going to solve this as a max flow optimization problem. This sometimes gets called sum similarity because they're trying to determine the similarity between things on the left and things on the right. And so in a situation where we're just considering the bids of people, we have here we have 3 papers, 3 reviewers. The first reviewer, bid that they really want to review paper A. The second reviewer said, I'd really like to review one A or C, et cetera. You sort of have some preferences that have been submitted. You solve this max flow problem, and you make an assignment, and you find that, okay, conditional on the fact that we don't want to overload any reviewers, we don't want to overload, and we want to make sure we get at least a certain number of reviews per paper, we're going to do the following assignment. So every paper here is going to get 2 reviews, and then they're going to submit the reviews, and you can solve this via sort of a standard linear programming solution. But a few years ago, a funny thing happened. So within a major CS conference, and this has been written about in the communications of the ACM, there was a fraud circle. So there was this cartel of reviewers that said, hey, let's get like a dozen of us or more together, and let's all just bid really with high preference on each other's papers and say we don't want to review anything else, and then we're sort of going to get assigned each other's papers, and we're all going to pat each other on the back, and we all get to go to Florida. Right? And so this actually happened. This was found out. There were sanctions from the ACM. And so Nihar Shah, who had been studying peer review systems, came up with this nice idea where he said, okay, let's bound the expected returns on fraud. So what we're going to do is we're going to modify the max flow problem, and we're going to say, yes, let's still try to get good reviews, but instead of matching sort of like finding the best possible match, for every paper, let's try to give it many candidate matches and say that we're going to sample from a distribution over matchings where no single person is guaranteed to get any single paper with a probability higher than, let's say, 0.8 or 0.5. So 0.5 is intuitive to think about. Essentially what happens then is that instead of picking the 3 best reviewers, you're picking the 6 best reviewers and sampling 3 of them. Now you have to do, the sample process is a little complicated. You have to sample in such a way that satisfies all the constraints so that everything gets 3 reviews. But there's sort of standard theory for this at this point that comes out of the sort of Birkhoff von Neumann theory of matching, or the matching polytope, et cetera. And so we can do this. And so Nihar and team, they implemented this system where you sort of can set this threshold of sort of like nobody gets assigned any single paper with a probability greater than 0.5, 0.8, et cetera. And this would be sort of what that would work out like. It's still an LP problem. And in their initial analysis, they showed that in terms of the objective function of the optimization problem, things really don't get that much worse, right? So let me see if I have a laser here. So if you start bounding the probability of anybody getting 1 paper, if you bring it down to 0.5, in terms of the objective of the optimization problem, you're really only paying a price of like a 10% worse solution measured by the objective function, right? So like you're getting pretty good matches in expectation, and you're sort of like hopefully mitigating this fraud problem. So this was implemented in Open Review. It's available to all the program committee chairs that run their conferences through Open Review. Open Review has become one of the leading platforms for running computer science conferences, sort of taken over the space dominated by EasyChair and some of these other platforms. And when I heard about this project before it had sort of reached the Open Review stage, I said, Nihar, you realize that you're effectively running large-scale peer review experiments. You realize that every time you're randomizing the peer review assignment, you're providing, there's sort of this enormous amount of randomness on the table that you should be able to interpret the quality of your assignments and sort of like the design of your system. You should be able to sort of like learn things about the design of that system from that randomness. So Nihar was super gung-ho, and we got the open review team on board for this. So this is sort of where things shift into a causal inference experimentation talk. So for those of you who haven't heard this little trick before, in the space of sort of understanding the design of various learning algorithms, there's this now classic paper, so classic that it got a Test of Time award at dub last year. And this is the Lee et al. 2010 paper. And this was a team working at Yahoo Research. And they were looking at the Yahoo News carousel. So this is the carousel of news articles. And you could show 5 news articles at any given time. And what it did was, instead of, they were trying to design contextual bandit algorithms that make good news recommendations. And they said, you know what? For a week of time, let's do totally random news. Somehow the product team agreed to that. And they basically just, it was like within a 1-hour window, and it was like not terrible. Like it had to cross a few quality checks. But they were basically shuffling what story got the top billing inside the news carousel. And then from that, they created this data set of kind of random assignment that they could then use to evaluate a whole suite of contextual bandit policies to try to understand sort of like what would be a good policy. So they collected this sort of under uniform sampling, and they could then evaluate a bunch of different policies, a bunch of different, using basically importance sampling. So in reality, you don't need to do this uniformly at random. But essentially what we're doing with the peer review setup is we're saying you've randomized some aspect of your assignment. Let's learn things about sort of like subsets of the data, when this happened and that happened, and reweight it according to the probabilities of all those events. The goal of the project here is to sort of harvest randomness and use that to learn things about adjacent policies. Recall that when I started talking about peer review, there's this whole design space about what are you trying to maximize? Do you maximize bids? Do you maximize the text similarity? There's sort of this whole configuration space that is the goal here to explore. So the first thing we did was we got on board this small workshop, the TPDP, which is a differential privacy conference. So it's a small workshop. They're looking at 35 reviewers, 95 submissions. We wanted to sort of pilot things and make sure we knew what we were doing. It turns out differential privacy scholars are very on board with randomizing their review assignment. Everything sort of worked there, and then we were able to get the AAAI conference committee, which is one of these enormous computer science conferences with 8,000 submissions and 3,000 reviewers, on board with running an experiment, with using randomization inside of their peer review assignment. One thing that's going to be a little bit sort of like, I'm going to under-deliver a little on, I'm not going to talk that much about the AAAI results because the design of that peer review match was very complicated in many different ways. So the AAAI peer review system, they were piloting many different technical innovations. That year, they were saying, let's make sure that every paper gets at least one senior reviewer, and then the rest can be junior reviewers. And that basically meant that there were like 2 matches, and we were only randomizing the first one. And it gets just sort of like kludgier to present that concisely in a talk, but it's all in the paper. So I'm actually going to focus on the smaller pilot, which is this differential privacy pilot. And the thing that we're going to be looking at within the confines of this talk is the sort of self-reported expertise, right? So this is when you, in computer science conferences, not only do you rate a paper, you also rate how confident you are on the review. And so arguably, love to talk about it, have lots of thoughts. A good outcome is one where everybody is saying that they have a high confidence for what they're reviewing. It would be weird to like maximize review scores. It's like, can we create like an all happy world thing? Like the outcome we care about is not maximizing everyone's review. It's like maximizing this sort of auxiliary confidence score. Okay, so, and we're going to be looking at that across, there's the assignment that happened, but then we're going to be looking at what would have happened if we did alternative assignment policies. So to unpack how these, the sort of the design space of peer review matching. So what we're trying to maximize is, for the vast majority of actual peer review and also within this talk, is just this some similarity for some choice of how we measure similarity or how we measure the score. So if these are some major, so NeurIPS, TPDP being a smaller conference, AAAI, large conference again, they have these kind of very fancy magic functions. which so TI is the text similarity, BI is the bid, and for NeurIPS in 2016, they did a 50-50 weighting of the text similarity and the bid times, the text similarity and the field similarity times 2 raised to the bid. Just like really magic number stuff. For AAAI, it was the same weighting of text and field similarity, or subject match field similarity, and then it was raised to the 1 over bid. And there's some logic here where with the exponential, they're trying to like create strata of how much like the bids that are higher bids should all be sort of mostly above. But by and large, it's sort of a lot of artisanal crafting. And so one of the projects of this, one of the goals of this project was to evaluate sort of like, there's all these weights, like how much do you weight text, how much do you weight bid, that we could sort of evaluate alternative ways to make that assignment, sort of turn those 0.5s into other values and understand how much would it change the quality. The other policy space we're going to evaluate is this sort of like cost of randomness. Sort of how much worse did the expertise get when we randomize? You know, because there is this like optimal match that we're foregoing in the name of preventing fraud. And you know, based on the objective function, we were only dropping 10%. Well, maybe actually like it's really sensitive to getting the best possible reviewers, or maybe it doesn't matter. And this was sort of an open question when we were looking at this, like how does objective function map to sort of like outcome? You're solving an optimization problem. That's not the same thing as measuring the outcome. Okay, so here's a fun technical problem that then became its whole second paper, which is that when you're randomizing, instead of just doing 3 papers per reviewer, you're up to like 6 papers per reviewer. So nobody gets the paper with probability greater than 1/2. So you're up to 6 papers. You only have like 6 possible matches out of thousands. You don't actually you're not actually randomizing like uniformly at random. Remember the news example? We could have sort of asked OpenReview to say, oh, let's do random matching, and that would have been sort of like a dead on arrival suggestion. That would have been even worse than randomizing the news, sort of the consumer experience of peer review if you're just getting completely random matching would be a really, really terrible one. So we only really have power to evaluate kind of like adjacent policies, right? We only like, you know, all the different ways that we could pick 3 out of 6, can we compare the ones that happen to pick a certain subset versus another? And one of the challenges here is that policies that we're interested in are going to put probability, or going to put weight on outcomes that our on policy is not ever going to show us. So we're going to have a lot of positivity violations. We're going to have a bunch of outcomes that we're going to be interested in policies that put weight on outcomes that we have no chance of observing. This data is censored, positivity violations, different words for sort of the same thing. However, we're going to invoke sort of a partial identification strategy that's going to get us most of the way. And thankfully, sort of like those, it's similar to Mansky bounding, but it's going to be based on some smoothness of some underlying functions. And that's going to give us, and not that much data is going to be unidentified in this way. And so we're going to be able to evaluate a bunch of policies. So the notation of the sort of technical problem, we have these units, and the units are paper reviewer pairs. I'm just indexing them by I, because otherwise you get this double indexing and gets messy. Every pair has a bunch of covariates. Z is our assignment vector. We're interested in these outcomes Y, which are self-reported expertise. And then there's sort of these 2 policies, the on policy, how we randomized, and then the off policy, which we're trying to evaluate. And we're interested in the expected value under the off policy, right? That's the policy we're trying to evaluate. But the assignment of Z was sampled according to the on policy. So there's going to be the bit of the estimand that we're going to be able to estimate because there's positive probability. And then there's the bit where there's a bunch of things that the probability under the assignment policy was 0, so we have sort of like no chance of estimating it. And one standard trick in this space is to sort of assume that the outcomes are bounded, use so-called Mansky bounds. Assume that, well, on the part that we can't see, the best case scenario is that everybody had perfect expertise. The worst case scenario is that everybody scored it with 0 expertise, and then we'll get an interval estimate. The forward pointer looks a lot like a laser. That's this idea of sort of like adding the plus and minus part of the estimand. What we're going to do here is that we're going to go sort of like one further and say that somewhat more optimistically, we think that there's a lot of smoothness structure and not just sort of this like worst case Mansky bounding. And here is how we're going to think about this smoothness. So what we're going to do is we're going to assume that this like expertise score is L Lipschitz in the underlying covariate space. So two units, two paper-person pairs that have very similar text similarity, bid structure, and field match vectors are going to end up, they're sort of like things aren't, the underlying mapping from that covariate space to this expertise outcome is going to be smooth. That's not the same thing as assuming the data is smooth, because the data isn't smooth. You're sort of like never going to get a small L on your data because it's jumping up and down, especially if you have a lot of it. But the underlying function is smooth. And much to our delight, as we've been working on this, there actually has been this flurry of other work under smoothness conditions, sort of Lipschitz conditions. There's that thing that is not a laser again. And so I recommend these other papers that are sort of like recent literature on partial identification under smoothness. Technical details are different between the papers. There's smoothness of the function, smoothness of the data, et cetera. And so essentially, there's a bunch of technical details in the ICML paper that came out this summer where we were able to work out, sort of show that, OK, so the big trick here is that while this seems technically difficult, it turns out that it all maps to a very tidy linear program where you try to maximize and minimize a linear program. And instead of doing your Mansky bound, where you just sort of assume the worst case and best case, or best case and worst case, you replace the values with the output of an LP that satisfies this like Lipschitz structure, and replace the lower bound with the output of an LP that satisfies the Lipschitz structure. And there's a bunch of sort of statistical theory in the paper for the fact that this converges to what we want it to converge to. So what the LP looks like is this is the minimization version where we're saying what's the sort of like worst case of what could things be here. And essentially what you're doing is you're trying to figure out a data point out here that has 0 probability. I want to replace it with the Lipschitz cone from the nearest data point, or the nearest point of the support, really what's going on. And so you have this, you're trying to figure out what these T's should be, and all the T's have to be Lipschitz with respect to the covariate space, and then they have to match the data where we have sort of positive support. And this LP is highly solvable, and it's so solvable that it's solvable in closed form, which is not something you usually get out of an LP. And how do you see this? You hire really good grad students. So Samir stared at this and convinced himself and then proved up this idea that the only constraint that matters is the nearest constraint, and it sort of reduces to a nearest neighbor structure. And you can see this from the dual and sort of like some more fancy ways to see this and sort of prove it up. But actually, the proof technique requires spotting it and then showing that it's the solution. So it's sort of one of these like proof by ansatz tricks. And we call this the no interaction property. When we looked for similar LPs with similar structure, we found another paper that had seen similar structure. And when it was in the reinforcement learning context, pointers to that paper for sure. But essentially, this LP is sort of solvable in closed form, but it's also like at a scale where it's not that bad to solve it for AAAI. So we actually were doing that before we figured out that we could solve it closed form. We were numerically solving these LPs over sort of like 8,000 assignments, 8,000 papers, 3,000 reviewers. And it was sort of computationally fine. There's a bunch of trickery here. If you start mixing like, oh, I think that the data is monotone and Lipschitz, things get complicated. Happy to talk about that offline if you're like really into the details of partial identification. So what happens? So what are our results for these when we've run this in the real world? So the first question I'm going to ask is this: like, what's the cost of randomization? How much worse did expertise evaluation get when we randomized versus when we didn't randomize? What's the outcome cost of this? And so the y-axis here is expertise, and the x-axis is this randomization parameter, where 1 would be that we're not bounding any probabilities, 0.5 meaning that we're doing this like half assignment. And on this we're comparing it to this like optimization measure, like how much did the optimization measure go down? And it turns out that there's a really, really flat landscape. And this also holds for the AAAI data. Essentially, the good news is that in the current structure of the peer review markets, if you view it as a two-sided market, there is expertise outside the top three. It's really not that different to assign reviewer 4, 5, 6 versus 1, 2, 3. There's actually this like weird little bit of a local maxima around sort of like not going for the very best assignment. Can't really explain that. But importantly here, we not only have sort of like the curve of what our off-policy evaluation is, we have it under a bunch of different assumptions. So the Mansky bound starts to be really, it becomes really hard to evaluate policies that are more randomized than us, because that means that we're putting a lot of probability on things that we definitely aren't seeing. But we have sort of like pretty limited need of assumptions when we're looking at things that are less randomized than us. And then we have sort of like different values of L or different values of the Lipschitz parameter. So what happens if you weight bids versus text similarity? So like if you're trying to maximize the text match versus maximize people's actual preferences. And here we see that the expertise scores definitely go up if you just max on text. You're just going to have a really unhappy review pool, right? So if you're ignoring people's bids and just matching them based on is their publication history similar to the paper, then you're going to get better reviews. But we're measuring, this is where the limits of like the expertise outcome starts to show its head, because arguably you're not just trying to create the best review expertise sort of like vector, you're also trying to have your reviewers come back next year, right? Because when you sign up to review, you get very annoyed if you get a bunch of papers that you didn't actually want to review. So that's where in the paper we analyze a bunch of different outcomes that are not just this expertise score. And here, having good partial identification strategies was important because particularly around as we get further and further away from where the actual experiment was run, it was run at 0.5, we get sort of these large Mansky bounds that sort of like blow up because there's a lot of missing data. One other thing, why is there sort of like an interval estimate to the on policy? That's because not everybody completes their peer reviews, right? Please complete your peer reviews. There's some fun technical details here where we said, well, okay, so like most of these optimized policies are all sort of equally good. There's not a huge difference. That's good news. That's good news. It turns out that if you're running a conference, it's not super sensitive how you set these magic number functions. They all kind of lead to good matches. But what we wanted to make sure that we weren't just sort of like, well, does any match matter? And recall that like we can't evaluate the worst match because that's way off of our data. So we did this little trick where we looked for like a misère policy. We said, what's the worst policy within what we have support for? What if we like strictly tried to minimize within the support of the on policy, find the worst policy we can evaluate well? And there we find that there actually is sort of like non-overlap between the intervals of what we estimate the values to be. So for AAAI, we're sort of looking at satisfactions around 3.3 versus 3.48. Like sort of like it is worse to minimize versus maximize. So a note on SUTFA. I've worked a lot on SUTFA assumptions. We are assuming SUTFA between units here. We're assuming that there's an independence between what other people were reviewing the paper is independent. Your score doesn't depend on who else reviewed it. That I think makes sense. The fact that your score doesn't depend on what else you reviewed is a strong assumption. Love to talk about it. By and large, I think this is sort of like one of these opportunities of sort of like improving a peer review machine, or improving peer review as sort of a machine that can be tuned. Sort of the idea of using policy evaluation and causal inference methods to improve the design of a system. In the paper, we also look at bandits and sort of like the original bandit problem from the 2010 paper. I'm out of time, so I'm conveniently reached my summary slide, but basically I view this as sort of like this idea of harvesting randomness is something that I would actually credit Dean to turning me on to. We wrote a paper in this space, and we wrote it in 2017. It came out in 2021. And it sort of like, it had a lot of influence on my thinking, and it was really, really rewarding to apply this through this system that, as an academic, I spend a lot of time inside. Thank you.
All right, thanks, Johan. If I can keep you up here for 1 second, and Sida, if you can start heading up. So I'll give you one quick question while we transition. You alluded to the sort of confidence being the metric that you chose to optimize, but there being arguments for others. I'm guessing many folks in the room, whether academics or practitioners, like spend some amount of time thinking about, we're running an experiment, what should our sort of like outcome variable be? So I'm just curious what some of the considerations were, or what some of the alternatives were that you thought about.
Yeah, so our main approach was we did the analysis with many different outcomes. So we also considered things like length of review, the heuristics that felt inferior. We played around a little bit with sort of like qualifying, labeling the quality of reviews through like an LLM. We didn't feel confident enough. We're academics, so we wanted to ground truth that against labeling, and we said, okay, we're not going to do that whole rigmarole, but those results look comparable. The real gold standard is that there are some conferences, not these, where essentially the editors, the area chairs, are asked to rate the quality of the reviews, and that's this like quality measure where that's arguably like an outcome that's even richer than self-reported expertise, which is full of a lot of delusion. So there are some other outcomes in the space of peer review. I still think they don't get at this like satisfaction problem. So I would be cautious to like go all in on maximizing any of those metrics, which is like often the multi-outcome space that a lot of problems live in. So yeah.
Got it. Cool. Thanks. All right. Thank you again, Johan. All right, and so now our second speaker in this plenary session is going to be Sida Peng, a senior principal economist at Microsoft, who's going to be speaking about the productivity effects of generative AI, looking at 3 field experiments with software developers. So I introduce to you Sida.
Thanks, everyone, and it's a pleasure to be here. Let me try the clicker. So one goes back. OK, great. Yes, so this is a paper that we had kind of worked for almost 2 years on 3 field experiments to measure the effectiveness of the generative AI on developers. Joint work with Kevin, Mert, Sonia, Leon, and also Tobias. Yeah, so so of course, like the product of interest here is this new kind of GPT, or the new AI technology that's just recently been introduced. And it turned out the name, the GPT, is very interesting. It's something that we can dig back in the history about the literatures and being mentioned even earlier in the econ. So as the earliest I can find here is 1995. They mentioned here the general purpose technology, right? So this is a GPT kind of not the same kind of abbreviation as the GPT now, but it's an interesting coincidence here. But effectively, they are talking about the same thing to some extent, about those technologies, whether those like steam engine, like electricity, those things kind of change our kind of generations and change the productivity, of course. The question here is really, is the new GPT the kind of the new form of the general purpose technology? And so this is what we are kind of trying to answer in this study, and especially like in real production environments. And there has been various studies that we have run, like even before the introduction of the, say, like those different Copilot products, to understand the effectiveness of the AI in more like lab experiments, right? So by running experiments, gather a focus group and partition them into a treat and control group to complete a task and see how effective the kind of the GPT or the Copilot products can improve their efficiency in complete those tasks. And over there, we have found like astonishing results that's due to the use of the AI. So the question now becomes, in real production, are we observing the same amount of influence to the productivity? or is there any kind of frictions? Is there any other factors that's going to be kind of influence those changes that we're going to come? So what we have done is that we work with like 3 companies, and we run field experiments on real developers in their real production environments. And the experiments involve around 5,000 full-time software developers. And we build pipelines. We can observe basically like their productivity-related metrics over a long period of time. So, and then why software developer? So I think this is to some extent related with the introduction of the product, and also what we find as kind of the most, at least the earliest kind of the implication of the GPT-related products. Like, of course, this is like on GitHub Copilot is first introduced for the developer and helping them to kind of do better coding. And on the other hand, it's also arguably the software developer is the new areas where the they power the kind of economic growth for the these days, and it's kind of cognitive and kind of demanding work. So most of the previous literature are more focusing on the non-correlative work, with exception of the like Bernie Snoff's paper on kind of studies the impact of the GPT on supporting agents and how fast they can kind of processing tickets. And here we are focusing on a different group, also a field study, and try to understand the impact for developer. And this can kind of help us understand another data points about how GPT and how this kind of new AI technology is going to influence the productivity for the developers. Yeah, and then lastly, of course, like another advantage or the reason that we run this on the developers is that the productivity or the output of the software developer is arguably relatively easy to measure compared with other knowledge workers. There are more standardized definition of unit works kind of defined by the version controls. Okay, so I think maybe most of the people here are already familiar with GitHub Copilot these days. Yeah, seems the video is not working, but it's basically code completion. It's in the form of the code completion tool. It helps you, but compared with all the kind of traditional code completion tool, it helps you generate paragraphs of code rather than just one line or like one or the next several kind of words in your code. So it's really building up on the context of the things that you previously type in, and then try to understand how this can help you. Yeah. So GitHub Copilot was released, first kind of released in April 2023. I think the product is actually being GA'd for around June 2023. And we were running the kind of the lab experiments back in the time. And then with the introduction of the Copilot for GitHub Copilot for Enterprise, that's launched in October, and this is where we kind of first started running experiments, further partner with our customers. But the experiments we run ourselves is slightly earlier. And I think back in the time when we do the study, the GitHub Copilot was powered by the GPT-3, and I'm also kind of impressed by how the version of the GPT has been being changed. So now I believe this is already kind of powered on the new new version of the GPT model. And then on the GitHub Copilot side, it achieved astonishing kind of adoption. Just within around like 3 months of the GA of the product, it reached to 1 million of the paid user. And then with the launch of the subscribers just in October, and in 1 month it reaches to 37,000 enterprise customers. So of course, this is also like a very highly competitive place where we're facing a lot of competitions from other companies. Yeah. So in terms of the 3 experiments we're running, so the first one we run ourselves. So this is the largest scale. This is a large scale kind of the controlled experiments we first kind of started. So around 1,700 developers are involved in this, randomized into a kind of a pure simple randomization into a treated and control group. And the treated group are allowed allowed access, the control groups are not. And of course, but on the other hand, we cannot force on the adoption, right? So this has to be kind of in willingness on people, they can kind of take it up by themselves. And the experiment started back in October 2022. So you can see this is even before the launch of the GitHub for individual developers. And the second experiments we're running, this is with Accenture. And over here, we have 311 software developers started in July 2023. And around 60% of the participants are in the treated group. And both the Microsoft and Accenture study are based on encouragement design. It's that because we cannot force on the adoptions, we send out rounds of emails and tutorials and help the the developer know about the product and start to onboarding them with and to use a Copilot. And then the third experiments we're running is with another anonymized Fortune 500 company. So over there, they have around 3,000 developers involved in the experiments. But due to the limitation on those experiments, I think a lot of the people, a lot of the folks here, in the tech company, must be kind of on the same boat with me. It's not easy to run those experiments really in product lines. A lot of frictions, compliance restrictions. So with the anonymized company here, what we eventually do, we cannot do a fully randomized experiments with them, but we eventually do is that because there's always going to be onboarding schedules, so we randomize the order of those onboarding schedules. So in different rings, there's going to be different participants, a random set of participants being allowed with the time. Yeah, so in terms of the outcome variables we're measuring through these experiments, of course, productivity is a very nebulous concept. It's this is something really, even for developers, although there's existing pipelines or more matured frameworks that we can talk about their performance or their work, is still something quite different. I should mention this is still something different quite from the productivity of the developer itself. Right? So a lot of things I'm listed here, like commits, pull requests, builds, and all of those are to some extent the metrics that we have this is all the metrics we can observe at individual developer level where we can approximate their output, right? So it's to some extent more like the effort provisioning for the developer rather than their real productivity, right? So this, some of those you may recognize are kind of notorious, in terms of kind of approximating in terms about measuring productivity. I believe none of the kind of the tech companies these days, big tech companies these days are really using those metrics as KPIs to measure their developer. There are various tricks kind of to play around with them. But I think because that none of those are used for those companies that we are measuring against, none of them are using those metrics as direct KPIs to measure developer, so there are less incentive for the developers to play around with those. So arguably in this case, they are better approximation for productivities in those companies. And and let me also kind of talk a little bit about the adoption about the Copilot over time. And this is basically the adoption curve, where this is what we kind of plot here on the Microsoft side. So the experiment started back in October 2022 with us. And this is a separation between the kind of treat and control group. Solid line is the treated group, and the dashed line is the control group. So you can see from the time the kind of the effectiveness of the pure controlled experiments runs from the beginning of October to the beginning of the April 2023, and this is where you can see the takeoff, the takeoff, the adoption of the control group starts. But in our analysis, we also bring in data that's after the adoption of the control group happens, and how to further kind of enhance the power of our analysis. As you can see, even in the January 2024, there's still a gap between the treat and control adoption. Right? So this by itself is another kind of interesting question about the kind of the potential frictions in the adoptions of those new generative AI technologies. Yeah, but this is kind of outside the scope of this paper. And you may notice also one of the, when we kind of launch the way we control for these experiments is that even for kind of internal Microsoft adoption, there is a tower, there is a kind of central control system where we can assign for the license of the Copilot. So not everybody is going to be assigned to the Copilot license at the very beginning. So we partner with the product team, and this is our engineer team. Like that, it's actually our dev team who responsible for the development of the IDEs, like a Visual Studio Code. So they are the first one kind of to try the Copilot. So we partner with their leadership and then like to control the license assignment for the tree line control group for all the developer in the organization. So at the beginning stage of the adoption, you can see there is almost like a flat kind of period of the time, almost like from October to the kind of the early February period. Here, like there's not much adoption taking off. This is this to some extent actually is a good thing for us, and to some extent is kind of due to a bug that's happened at that time with the compatibility of the Copilot and the Visual Studio. And the engineering team is kind of trying to focusing on fixing that bug, so we didn't really kind of further help drive the adoption, like using emails, nudgings, and so on. So that's why you're seeing like there is a flat line here in the initial stage of the adoption. But the treaty group are still allowed to adopt Copilot if they find out that from their colleagues, from other sources that they may have, they may still able to kind of jump into Copilot. So there's still some people adopting over there. This, to some extent, like get us kind of extends our experiments further longer, right? So one of the, you will see like in our estimates, one of the biggest challenge that we're facing in evaluating those field experiments is that there's power issue, right? So in these experiments, because of also the kind of the low adoption rate at the beginning stage of the introduction of the technology, directly kind of comparing the treat and control group may not get you any results. So we really kind of want to focusing on the group who adopted, and then kind of extrapolate on top of them to understand basically what's the effect, what could be the kind of potential approximation to the average treatment effect. And this is kind of on the adoption on the center side. As you can see, this is a kind of much clean version of the control of a randomized control trial. So we only have kind of adoption in the treated group, and we started the experiments from July 2023 to October 2003. And this is, and the reason here is that this is a relatively small population of the developer, only 300 of them in the experiments. So it's much easier to control the access of this group and getting commitments from the business to further run it, to run it strictly. And lastly, this is with an anonymized company, where over here you can see the adoption. We won't be able to kind of achieve a fully randomized control trial, but we are able to randomize the rings about people to get in. So the solid line here is for the treaty group, and where the timing that they get access, you can see this is kind of staggered, but this is only kind of to some extent restricted with this 1 month period of the time. That's kind of the best we can negotiate with the customer to run this experiment. So yeah, so that's kind of to some extent like the biggest challenge in running those experiments is that we have to adaptive to the rhythm of the business and also the need from our customers, so that we can really not delay too much like on the adoption just due to run those experiments. Yeah, so this is our empirical strategy on evaluating the impact. Of course, as I mentioned, like one of the biggest challenge here is that we cannot just, if we simply kind of compare the average of the treated group and the average control group, it's we don't find any statistically significant evidence in terms of the effect of the product, purely because we are working at a very early stage of the adoption of the technology. Adoption rate is low, so we cannot, all of the effects calculated there are diluted. So what we are further looking into is among the people who actually adopted and trying to understand to some extent the late effect, local average treatment effects, right? So using the instrumental variable approach. And here the experiment itself, or the kind of the timing of the randomization of the timing of the adoption, effectively become our instruments. And we're trying to use these instruments to understand the effectiveness of adoption of the Copilot and to all of those different various outcomes on the productivity. Yeah. And also, we further enhance the, we also present you the results on the so-called weighted IVs, where we want to kind of shift our weights to, because we're really dealing with a time series of the adoption pattern and also on the productivities. We really want to kind of focusing on the period where we have the most identification powers, where the randomness actually happens. And this is where we kind of reweight some of the period in the adoption. So you're going to see both results from the IV and also weighted IV. Those are all standard technologies in the literature. Yeah. So this is the effects coming from the. This is the mean results we have coming from this 3 different companies and also their pooled results. So as we can see here, there is just kind of coming from the pooled results. There's around like 26% improvement in all of those numbers are in percentage, and there's 26% around 26% improvement in the pull request, and also there are statistically significant improvements also like in the builds, and if you further look into like some of the segregated effects like within each companies, you can see some of them start to kind of showing statistics, also kind of showing statistical significance. Right, so I should mention here, like this is all like this is all weighted IV results, and the IV results you can check those out in the paper that we released. Yeah. So while we are also kind of observing those difference, like for example in Microsoft, like the pull request number results is significant, and also on the Accenture side, like the build results is significant. I think to some extent, like those different metrics here also represent different cultures in the work within different companies. So for example, within Microsoft, we know that the kind of the pull requests sometimes go hand in hand with the commits. So, and in this case, when developers kind of finish a task and they were immediately kind of submit the commits, and then they were submit the commits and then first submit the pull request. And this is where we saw the significance of the completed task. The results is more on the kind of the pull request side. And also on the Accenture side, I think what we hear is that their task of the work is more happening at the team level. So there may be a lot of builds done locally by the developer and a lot of kind of commits done by the developers first. And then only until say like the end of the week or when the project's been concluded, and this is where the team leader will kind of submit the last pull request, and this is where we are seeing, I guess, like a less kind of results on the pull request side. Yeah. Yeah, and also the other thing I want to point out here is that, as you can see, the standard error for those estimates is to some extent really big, right? So we're dealing with really kind of noisy estimates here, and I think this is to some extent the challenge for the field experiments and with all of those pipelines that and in together with also like the early adoption and those diluted results, and this is like all the kind of challenge we're facing in evaluating the effectiveness of Copilot in this early stage. So summary so far. So from the results, we are seeing an increase in the productivity of software developer. And the limitation, of course, as I mentioned, is that the productivity measure or the outcome measure here are not really productivity. And those are to some extent all approximations to the productivity. And so, and our findings here is also consistent with existing study and also consistent with almost consistent with the existing study, like on those different lab experiments. And for sure, like in those lab experiments, we're finding bigger results, bigger effects. And because this is more focusing on kind of finding the productivity improvement on a specific task, but and then in productions, developers are not coding 100% of time during their work, right? So they also need to kind of take meetings and distracted by other activities from the companies. So effectively, the effective coding time is definitely lower, and so that kind of maps out to here, like around like 20% improvement in their productivity. And yeah, next I'm going to show you, like in the last few minutes, about the heterogeneous treatment effects we're further kind of looking into, and yeah, because the kind of the estimates of the effects is really noisy, we're trying to kind of further partition down to understand where the variation is coming from. So one of the places where we're finding difference among, there's definitely like more places where the heterogeneity can happen, but this is like turn out to be like one of the places we're looking into, which is on the tenure of the developer. So for Microsoft data, we also observe the work histories of our developers with us. So over there, we can kind of separate them by the kind of long tenure versus short tenure. So the break point we're taking is around 3 years. And here, first, you can see the adoption pattern between the short-tenured engineer versus the long-tenured engineers. You can see a clear difference. There's definitely more enthusiastic and the passion of the adoption coming from the short-tenured developers. And in terms of the acceptance rate coming from the Copilot, you can also see like a clear difference. For the short tenure developer, you can see almost like 24% kind of acceptance rate of the recommendations coming from Copilot, compared with around like 22% coming from the long tenured developers. Of course, I mean, there is a difference in the experience level, right? So we know, also kind of building on like existing kind of literature, there is a known fact that junior kind of developer kind of benefits more from the Copilot than more senior folks. And this is our finding here, our results here are consistent with those previous studies. Yeah. And this is kind of the further effects on the total pull request for the kind of further separated by the short tenured versus long tenured. As we can see here, the major effects here is actually concentrated from the short tenured developer. And also, this is like here the percentage increment on the pull request is almost like 55%. And on the other hand, for the long tenured developer here, the results is close to 0. So also similar results like on the commits and on the successful builds. And over here, this all kind of consistent to say like the impact of the Copilot is more focused on the short tenure developers. Yeah, so I have 1 minute left. So this is the kind of just to conclude here. So what we find here is that what we are doing here is evaluating the impact of a large language model through the lens of coding. And here we are finding very noisy estimates, but still kind of significant and consistent positive effects, around 26% increase in the completed pull request. And also we are finding the heterogeneity here. There are higher effects for the early career developers. And this is consistent with kind of the builds from the existing studies. And yeah, this is it. Thank you.
Awesome. Thanks, Sida. And you should stay up here because now we'll do Q&A
Sure.
with Johan as well. While Johan is headed up, a question for you, I guess. One thing I was thinking about as you were presenting the results is the possibility of SUPA violations. So even though the control developers in your study can't access Copilot, you can imagine higher or lower quality, I guess, pull requests are being submitted by treated developers, and then someone else is reviewing the code or something that provides a channel for spillovers. But I also noticed in the slide with your results, I think there was an allusion to clusters. So I was thinking maybe you did cluster randomization and not individual level randomization. But I guess I'm just wondering how you've thought about the potential for SUPA. Maybe there's cluster randomization in the experiment.
Yeah, like we'll kind of try to do some clustering like to account for those for sure. And but like in terms of the the clustering is done at the team and kind of adoption cohort level, right? So and then like for the spillover, but the randomization is done at individual developer level. So for the spillovers, of course, that exist, right? So if you developer kind of submit for pull request, there's going to be reviewers review their code in the team. If that adopts the Copilot, that will also kind of benefit them in the process, right? But those are things that we're not able to kind of really control, like from the study perspective. It by itself is definitely an interesting question, right? So even kind of before the answering the question about on the productivity side, even on the adoption side, there's also like notably kind of spillovers in terms of the adoption. So it's a complicated question, so we don't have a good answer on that.
Cool, thanks. All right, I have kind of unfair questions that I want to ask both of you. So I'll start with Johan. So I guess I'm looking for connections between the two papers, which naively, maybe are not the two most related projects. And one thing I was thinking about is in addition to thinking about fraud, presumably in the peer review process, just the advent and ubiquity now of generative AI is probably going to affect how conference organizers think about, just reviewing papers, the volume of papers that are submitted, so on and so forth. I know I have some colleagues at Berkeley that have been looking at, adoption of generative AI tools in academia. It seems like there's a lot of authors that are starting to use these tools to write abstracts, help writing papers, things like that. I guess, Johan, do you have any thoughts on how peer review might change given these tools, both in terms of organizing peer review, but also just thinking about new vectors for, fraud and bad science and things like that?
Yeah, so I'm in a situation of knowing that I don't know. So I know there's a lot of work in this area that I don't have fully on my radar, but there's sort of like good and bad things going on for sure. So there's obviously the concerns about bad faith reviewing, where people are kind of like just dumping it in and having kind of like some LLM write the review for you. And how to catch that, and that gets into the whole like watermarking, fingerprinting debate. I think like a really sort of a positive story is that, so James Zhou at Stanford has done some work where they basically encourage people to like get a pre-submission review out of an LLM, right? So submit your, and all grad students should be doing this, or all scholars should be doing this now. Take your paper, ask an LLM to write, to give you feedback, to simulate a review, and it's basically the equivalent of like an immediate friends and family review that you would normally like ask some colleague to do. And it's often non-trivially useful, so I really recommend it. I have fortunately not chaired any peer review, any conferences in the last 18 months, so I haven't had to deal with the reality of these things, but I know that it's challenging, and yeah, circling back to like know that I don't know, there's a lot going on there on both sides. Some conferences are experimenting with like having an LLM in the review, and sort of like saying, no, all y'all humans like do a human review, because we've already got the LLM review, and we're gonna make it available to all the other reviewers. There's very interesting things happening. They're not sitting on their hands for sure.
Cool. I didn't know about a lot of this, so that's super interesting. And then, Sida, I guess, so not the paper you presented today, but I know you have a different paper that you're a co-author on that looks at open source software development and access to Copilot-like tools. And that paper, I believe, is not a randomized experiment. It's more of like a regression discontinuity design where there's some threshold determining, who gets access to Copilot and who doesn't. And so I guess you could think of that paper as being, an example of, to use Johan's terminology, mining randomness, where, you don't randomize in that case access to Copilot, but there is some natural randomness arising in the world in the proximity to that, that access threshold. And I'm wondering if you have thoughts on, what can we learn in cases where we don't randomize, but maybe analyze a natural experiment versus a case where we have a randomized experiment. And you're sort of in this situation where you have two different, research designs, I guess, but you're asking similar questions about a similar phenomenon, maybe.
Yeah, sure. So we run a lot of those studies, and there are definitely like pros and cons like of each scenario. So we really kind of try to understand the situation like from different aspects. And you're actually like going to see that paper like from Frank's session, I believe, tomorrow. So yeah, like over there, like we're more like taking an observational kind of approach, observational study approach. So I guess the kind of the pros from the experiments is that it's always kind of the most objective measure to answer the causal effects, right? So, but the kind of cons of the experiments is that the efforts and the cost of executing that is really high. So only in like very with paying a lot of costs and understanding in the kind of the most super situation, and that's kind of where we can run it and get the kind of the impact of the true causal effects. And in most of the cases, and especially like in the open sourcing world where there's the kind of not much too much space for us to do the randomization, and or like the cost kind of maybe just too high, and in that case, the best way that we can approximate the causal effect is through observational study. That's the only choice we have. And this is, to some extent, like to understand the impact from different audience, different outcome variables, and thus kind of require us to run those experiments on the different situations. And this is where we kind of have to choose and weigh kind of the pros and cons of different methodology and choose the most suitable ones.
Cool, thanks. This seems like maybe a good moment to open it up for questions. So if you are out in the audience and have a question, raise your hand. We have a couple of mic runners in the audience who will find you and bring you a mic. All right, looks like we have a first question right over here.
Yeah, so the study that you ran with Microsoft at Accenture, there's a very clear correlation that junior SWEs, they got more productivity gains versus senior SWEs. Do you see any difference, like if, assuming that the GitHub Copilot is improving and now it's grounded in my enterprise data, is this a function of like the GitHub Copilot not being mature enough? Or is it just that, people with more tenure tend to do more complex tasks and that's why we are unable to help them?
Yeah, so I would say there are definitely kind of factors around that. So, but also bear in mind that we are evaluating the experiments at the very early stage of the Copilot adoption, right? So all of the experiments took place like in 2023. So, and the method or the kind of the AI model behind is only GPT-3. So, and now with kind of GPT-4, we are more kind of gearing towards the next generation of the GPT. So I believe there is going to be like a performance improvement over there. And potentially we will see, we should be able to say like more complicated tasks will be benefiting from the use of the Copilot. And in this case, I would expect that the more senior developer is going to benefit more.
Cool. Just quickly, while we're on the topic of heterogeneity, Johan, I guess I'm curious, in your study, I know we saw a lot of like overall results, but did you look at all at using these off-policy evaluation tools to look at, for instance, how confidence maybe varied for different subsets of the population that's doing the reviewing? I'm not sure if you have the data to look at this, but I can imagine certain subsets of reviewers are more or less affected by different matching approaches.
That's a great question. Short answer, we didn't. The differential privacy workshop was small, so there wasn't really that much to split on. For the AAAI, on the randomized part, we're really only sitting on one review per paper, so going to heterogeneous would be hard. I mean, I actually think that that's a place where like the cost of randomization becomes a concern because there are certain it's ultimately, peer review is ultimately a market which has a lot of like clustered structure. You could think of it like a bidding ad market or something, but there's certain specializations within a giant conference, like, within NeurIPS, there's the people who do differential privacy, there's people who do visual, NLP, sort of all these different things, and there's sort of sub-markets, and you could be concerned that one of those is more susceptible to sort of like expertise down, like reductions on the review than others, but it's not something that we looked at.
Cool, thanks. Looks like there's another question out there.
Yeah, for the Copilot, it was like contributions were up in terms of like commits, but it looked like the build fail rate was also a lot down. I'm just curious how those balanced out. Like, was it a net neutral or net positive?
Yeah. So I think those are effectively talking about like different levels of the contribution, right? So to some extent, like a build is something the developer can just like run on their local machine and kind of to compile with their code and just try to see what's going on. So there is indeed like a tendency that we observe from the kind of more submissions like coming from the use of the Copilot. So when it can generate user code faster, of course the first thing you want to do is just to do a quick build and just to say whether it kind of passed it successfully or not, right? So I think that's kind of the major effect, especially in the early stage, where when with the GPT-3, there's still like some hallucination issues, like with the Copilot back in the time. So that may just generate a code with some bug, right? So and in that case, if you just quickly do a build and you failed, right? So I think that's related with like how the kind of negative effects we're seeing on the build side. Yeah, but effectively, this is still about, I would kind of put more weights like on the commits and pull requests here as approximation on the tasks level. And then in this case, we're still kind of seeing savings around the improvement on that.
Okay, is there another person over here maybe? Yep, okay.
Yeah. On that question, as a follow-up to that, did you run a similar heterogeneity analysis of the build failure rate by developer tenure? Because I could imagine two scenarios, one in which the Copilot acts as support for the junior developers in encouraging them, in emboldening them to actually check in the code and go further. But I could also see an alternative scenario You could call it a children of the Magenta Line scenario, if anybody recognizes that, where they check in any old slop that comes out of the AI because it gives it an air of authority. So, do you have and it strikes me that as the build failure rate is a quality metric, do you have a breakdown by tenure?
Sorry, can you repeat the main question?
Do you have a heterogeneity analysis of the build failure rate by developer tenure?
Yeah, I think you can find that out from the paper. I don't recall the kind of the exact results we have, but this is definitely like an area that we further dig into and understand basically like how that different across the kind of the junior versus senior developers.
Yeah. Okay, Vida?
Yeah, a question to Johan. So one thing that was interesting, I think more of a maybe qualitative question. So your outcomes were different whether you were optimizing based on the bid, which is like the reviewer preference, versus text, which is the reviewer's expertise. That's an interesting difference. Like, why would the reviewer be interested in reviewing papers that are different than their expertise? So did you look into this, like why there's such a difference, and particularly from the reviewer side?
Yeah, so for me, it actually made a lot of sense based on the following understanding of myself, or whatever, sort of like introspecting. So when you upload, the way that the NLP match happens is that you either upload or connect it to some profile, upload a set of papers or connect it to a profile with a public repository of your papers. And that is a kind of like backwards looking view of what you're good at. And so with all love for configuration model random graphs, I get asked to review a lot of papers on random graphs. And I haven't worked on them in a few years, but I have a bunch of papers in that space. And so it's sort of like there's some expertise that you have in your background that you're not actually that excited about reviewing, but you are really good at it. So I think that that's really the trade-off, whereas the bid is, I might not have published a paper on XYZ, but I'm currently working on XYZ, and I want to read papers on XYZ, and so I'm not a bad reviewer for XYZ, but then again, we see that does map to sort of slightly reduced confidence scores compared to people who have been working in XYZ for a while based on their published papers.
Looks like we have another question.
Yeah, a question over here for Sida. Did you look at code coverage improvement? Because I don't know about everybody else, but writing unit tests is a pain. And ChatGPT is actually really good for generating a ton of unit tests. I'm curious if you looked at that.
Yeah, this is actually a very good thought. This is something we only able to do like in those large scale experiments, because unit test is something really not being well documented. Right, so it's not, we cannot really kind of tell like whether this pull request is about like, or this build is about like unit test or it's not. So, but this is indeed something we're currently thinking about, like understanding basically the impact of Copilot on code quality. So those are definitely on our research agendas. Thanks. Yeah.
Great. Is there another question out right here, I guess, maybe? Yeah, cool.
For Mr. Peng, this is kind of an unfair question to ask, but I understand that the paper is coming more from the point of evaluating the efficiency of code writing itself, but have you I guess, considered any plan about the outcome more in terms of the improvement in key aspect of the project itself, like KPI or things like that? And I do see that it kind of will be a messy problem, because in terms of treatment, you can encourage different project team to adopt these code pilots method, but then it's up to the individual within the team whether or not they will pick up the copilot themselves. So yeah.
Yeah, indeed. I think those are all very interesting questions, and those are all questions we would like to know the answer, and especially about like talking about the impact of Copilot really at production level, as a project level, right? So to some extent, that require maybe like randomization across kind of projects, and talking about say like what's the impact of Copilot on say like the kind of maybe the impact on or efficiency on the completing a project itself, or like whether it has any impact on the security compliance of the project. Yeah, but those experiments really require large scales, right? So even in Microsoft, like there's, I guess like maybe like 10, if for small team, maybe 5 or 10 developers working on one project. For larger team, there's like maybe hundreds of developers working on the same project. So doing randomization there is really challenging. I think maybe observational study is the only kind of a possible route, which is indeed like something we are interested.
Great. I think there's another question, or there's a couple of microphones. Let's start with Daniel, and then we'll.
This is a question for Johan. So now that there are these randomized experiments for peer reviews, like, are there sort of possibilities to sort of look at further tweaking them, say like getting more information about the reviewers, or like later seeing the success of papers as another like quality metric or things like that?
Yeah, great question. So I think it's also worth, I had them up on the slide, but it's also worth acknowledging the like genuine A/B tests that have been run within the peer review space. So Wisdom ran one, which is a CS conference where they randomized that are sort of like outside the space of the design space that gets accessed by these randomization strategies that I talked about. For example, the Wisdom conference, they randomized whether or not the matching was double blind or not, because there's a debate within the CS literature about like the value of like author identity as a routing like information like search problems, et cetera. Is it good or bad? Does it lead to bad things? And so they had half their peer review pool do bidding with or without the identity of the authors, right? So that's the type of thing that's not accessible unless you were to it's not accessible by the randomization that gets added to prevent fraud. So those types of A/B tests are still very valuable, and I think that there's like a broad like design space of peer review. Again, there's also the big like NeurIPS experiment where they basically doubled up the review pool, extraordinarily expensive in terms of like the human labor involved, and then they, out of fairness, like any paper that was accepted in either of the two parallel universes was accepted. I was an area chair for NeurIPS that year, and it was a very interesting experience because I got this email after the fact where it said, hey, a paper that you were area chair for was accepted in the parallel universe and rejected in your universe. Do you have any qualitative comments to add? And I was like, oh no, like, am I the baddie? Like, am I the area chair that didn't do due diligence? But when I looked at the 3 reviews in the parallel universe and the 3 in mine, all 3 of mine were below the bar. All 3 of those were above the bar. And that was just like wild to me that could even happen. Now we're selecting on the outcome that there was a split. So like, but I got sort of like one of the worst draws in the batch, right? In the sense that it was really hard for me. Like I'll be honest, I didn't go searching for an argument to accept the paper when I saw 3 reviewers who all came below the bar. So there's a lot, and that was an opportunity to measure like the sources of variance on acceptance, and then what does that mean for outcomes of sort of like how papers are picked up. I think there are some additional outcomes that are planned for some of those A/B tests where people are like basically tracking that cohort of papers in time that will give us knowledge. So there's a certain like there are fence posts on how much on the design space that you learn about by randomizing the actual match. And there's like a broad space of questions that are interesting that are causal about peer review that I think A/B tests are still really valuable for. Yeah, we were interested in evaluating like improving the Toronto paper match system and replacing it by LLM matches. But when we were running this, like the LLMs weren't quite good enough. So we could go back and redo that analysis because we have all the papers and all the everythings. And basically, like, what's the value of improving the NLP is like one question we had. There's definitely other questions for sure.
Cool. I think we have time for this might be our last question. I saw a mic right here, and then if we have time for this last one back there, we'll do it. So, all right, go ahead.
Super quick, but it's for Sida. Your adoption measure was week of first use, right?
Yes.
Is there information on continued usage throughout the experiment?
Yes, we do.
What is the dropout rate on average? Is it similar across companies, or?
I guess, I mean, depending on how you define dropout, right? So this, I don't know like the kind of a good benchmark on that, but there are definitely kind of people churned. Yeah.
All right, cool. And let's take one last question in the back of the room back here.
Yeah, that question for Sida, or I guess either, but do you have thoughts on expanding experiments like that to include measures of developer satisfaction with their job, or retention, because I think what a cool way to kind of pair the productivity research with how do we increase developer happiness with generative AI.
This is definitely an interesting area, though there are definitely like a couple challenges on that, right? So getting HR data is the most difficult thing, I think, within a company. Yes, and but I think also like with all of the introduction of all those different technologies, I think like to some extent when we run experiments, we were lucky because at that time, GitHub Copilot was the only AI-powered coding tool, right? So people cannot look into like ChatGPT or like other kind of Copilot products and to find answers. But not these days, even though we can control their access to GitHub Copilot, there's all other sorts of Copilot we need to control. So I think like on the further down the road on the experiments, it will be more reliant on the observational study side. Because on that side, this is maybe the only thing that we can approximate the causal effects these days.
Yeah, and in addition to developer happiness, I think code reviewer happiness, to connect to Johan's work, is probably also something to look at, since if a bunch of bad code is getting submitted in a pull request, the reviewers are probably not too happy. So that's also an interesting question. All right, so that takes us to the end of our first plenary session. Let's again thank both of our speakers for amazing talks.